Section 3.2, Polynomial Functions and their Graphs. So the three learning targets here, determine end behavior of a polynomial. This has to do with the shape of the graph, which we'll talk about. And that's important to determine that end behavior before we get to the second learning target, which is graphing a polynomial. And then we'll talk about the relationship between zeros, factors, and graphs of a polynomial. So we need to start, though, by talking about what is a polynomial. So polynomial functions. The word poly means many. Nomial you can think of really in this case as terms. So polynomial literally means many terms. So a polynomial function is a function that's the sum or difference. So you can see here that these terms are adding together. So it's really just the sum of a bunch of terms. And I know it's looking at this, you're thinking, well, this is confusing. What are the a's and the x's? So the x's, those are just your typical variables. So x to the n, and then x to the n minus 1 would be an exponent that's one less than this exponent. For example, if we started with n equals 4, so x to the n would be x to the 4th, and then we'd have x to the 3rd, and then an x squared, and then this would be x to the 1st power, and then we'd have this last term here. And I've tried to explain what some of these things are. So we have a term here, we have a term here. Those are all terms. A term comprised of a coefficient and the variable to the exponent. That's the term. So a term is comprised of the coefficient with the variable raised to an exponent. So the a sub n and the a sub n minus 1 and the a sub 1, these are just coefficients, and coefficients are numbers. They could be positive numbers, they could be negative numbers. Typically they're whole numbers, but they don't have to be. They could be fractions. So the coefficients are just the numbers that are in front of a variable multiplying the variable. A sub 0 is the constant at the end. It has no variable, which is why it's called a constant. Now some characteristics of polynomial functions, all of the exponents, so n and then n minus 1 all the way to x to the 1st power there, all of the exponents of a polynomial have to be positive integers. Integers is a whole number, so they have to be positive whole numbers. No negative exponents, no exponents that are fractions. So that's one characteristic. Another characteristic of a polynomial function is that the graphs are what are known as smooth and continuous. Continuous means that there are no gaps or holes or sharp corners. Well, that's what smooth means. Smooth means no sharp corners. So continuous means no gaps or no holes or no breaks. If you remember, for example, in chapter 2 when we did piecewise functions, those graphs are not continuous because they're broken into several pieces. And there are gaps in those graphs, but a polynomial function has no gaps, no holes. So they're considered smooth and continuous. So I've got some examples here to look at of some polynomial graphs and polynomial functions. So we have y equals x minus 1. This is a polynomial function. We know it's called linear. It's a linear function, but a linear function is a type of polynomial function. So x minus 1, linear, but it's a polynomial. You can see the graph here. It's a linear graph. I'm sorry, I meant to point this out. Going back up here, the largest exponent of a polynomial is called its degree. So for example, if the largest exponent of this polynomial would have been 4, then we would say this is a degree 4 polynomial. So you can see I have written under each one that the highest exponent of the variable here is x to the 1st power, so this is called a degree 1 polynomial. Now this one here, this is a quadratic. It's called a quadratic function, but it's a type of polynomial. So this is a polynomial function, and because the highest exponent of the variable here is 2, this is considered a degree 2 polynomial. Here we have a degree 3, and here we have a degree 4. So these are all just examples. And what I mean by smooth and continuous, you can see that there are no breaks or gaps or holes or sharp corners in any of these graphs here. So one characteristic or one item to note on a polynomial is what is the degree. The degree of the polynomial is the highest exponent. Now we're in this first learning target now of discussing end behavior of a polynomial. And end behavior of a polynomial describes literally what the name says, the ends of the graph. For example, here's one end of the graph, and here's the other end of this graph. So these are called the end behaviors. For the second degree polynomial, here's one end of the graph, here's the other end of the graph. Those are the end behavior. And what I like to do, and that's why I've got some little graphs down here, for a degree 1, or at least this picture that I've drawn, if we discount the middle part of the function and just look at the end behavior, the right side of the function and the left side of the function, the right side of the function is going up to positive infinity, the left side of the function is going to negative infinity. But when we come over here to this second degree polynomial, the right side of the function is going up to positive infinity, and the left side of the function is going up to positive. The right side is going up to positive infinity, and the left side is going up to positive infinity. But if we come over here to the third degree, again, the right side is going up to positive infinity, and the left side is pointing down to negative infinity. If we come over here to this fourth degree polynomial, the right side end behavior is going up to positive infinity, as well as the left side end behavior is going up to positive infinity. What I'm trying to get at here is recognizing a pattern. If we look at the degree of the polynomial and then the end behavior of the left and right side, hopefully you can see a pattern here. And it has to do with whether or not the degree of the polynomial is even or odd. What I mean by that is, if you look at a degree 1 or a degree 3, those are both odd degree. They have similar end behaviors. The graphs look a little different, but in terms of the end behavior, the degree 1 and the degree 3 have similar end behaviors. And same thing with a degree 2, which is an even number, or degree 4, which is also an even number. They have similar looking graphs, but more importantly, it's the end behavior that's the same with these polynomials. And so the connection here is the degree of the polynomial determines the end behavior. And whether or not they have end behaviors where the left side of the graph and the right side of the graph are going to the same direction, or if the right side of the graph and the left side of the graph are going in opposite directions. Now, one important thing to keep in mind, for example, with this polynomial right here, if I put a negative in front, that flips the graph upside down. Let me repeat that. If I had put a negative sign in front of this polynomial, that would have flipped the graph upside down, which would mean that the end behavior on the left side is going down and the end behavior on the right side is going down. Same thing with this polynomial here. If I had put a negative sign in front of the polynomial, that flips the graph upside down, meaning the left side of the graph is going to negative infinity and the right side of the graph is going to negative infinity. Similarly, with next to the third, if I had put a negative sign in front of this polynomial, it would have changed the function to look like this. So now the left side would be going up to positive infinity, and the right side would be going down to negative infinity. Now the point I'm trying to make with this is that whether or not, going back to this x squared, for example, whether or not it's facing up or facing down, if it has an even degree, the end behaviors are traveling in the same direction. So either they're both going up to infinity, or if it's an upside down graph, it's going down to negative infinity. With an x to the third, if it's a positive leading coefficient, the right side is always going up to infinity and the left side is always going down to negative infinity. Or if there's a negative sign in front, it switches. The left side is going up to positive infinity and the right side is going down to negative infinity. That's if it has an odd degree. So the degree of the polynomial determines the end behavior, and that's an important piece in shaping the graph, in figuring out the shape of the graph. Now there's a particular way of stating the end behavior, and it has to do with what x and y are doing. So for example, if we're looking at these points on the graph, and if I continued this indefinitely, the x values are approaching positive infinity, and the y values are also approaching positive infinity. So the end behavior on this side of the graph is x approaches infinity and y approaches infinity. If we consider points on the other side of the function, so these points here, we would say x is approaching negative infinity and y is approaching negative infinity. So that's how you would describe that end behavior. Coming over to an even degree function though, so this x squared, if we look at these points on the right side, x is approaching positive infinity and y is approaching, so the x and the y values are both approaching positive infinity because the x values are going this way, the y values are going that way. On the other side of the function, here we go. This side here, it is still true that the x values are approaching negative infinity. So we would say x is approaching negative infinity, but now the y values are approaching positive infinity. So x approaches negative infinity, y approaches positive infinity. So that's technically how you describe the end behavior. So as an example, determine the end behavior. We don't need to see necessarily the graph in order to determine the end behavior. What we need to know is what is the degree and what's the leading coefficient. So the degree of this polynomial is degree 3. That comes from the highest exponent. So we know it's a degree 3. Now the leading coefficient though is 2. So what is going to result there is it flips the graph upside down. That's going to be a vertical reflection. So a third degree polynomial has a graph that looks similar to this with end behavior, but the end behavior is going to switch from this because we have a negative leading coefficient. And so coming back here, rather than graphing the entire graph, I like just to have a picture of what the end behavior would look like. So because we have that negative leading coefficient, I know that the left side is going up to positive infinity and the right side is going down to negative infinity. So the way we would describe that is x approaches infinity, y approaches negative infinity over here on this side. And then over here, x approaches negative infinity, y approaches positive infinity. So that's how you would describe the end behavior there. With this one, the degree, it's a degree 4 because that's the highest exponent, so I know it's a degree 4, and it has a positive leading coefficient, meaning it has not been reflected vertically. So a 4th degree polynomial has a graph that resembles this shape, particularly the end behavior. Since it's an even degree, the end behaviors are both going to the same direction. So the right side and the left side of an even degree polynomial are both going in the same direction, whether it's positive infinity or negative infinity. In this case, it's going to be going up to positive infinity because we have a positive leading coefficient. So the right side is going up to positive infinity, and the left side is going up to positive infinity. Now in between, it's common that we have a few ups and downs and things like that, but at least the end behavior we can be sure of is its left side's going up, right side's going up. So here we would say x approaches infinity and y approaches positive infinity. Over here on this side, we would say x approaches negative infinity because it's going in this direction now, and y approaches positive infinity. So this is what it means by determining end behavior of a function, of a polynomial function. Now we have our second learning target, which is graphing a polynomial. And there's three things we need to do in order to graph a polynomial. We need to know the x-intercepts, and those are called zeros, and I'll explain a little bit more about that here in a second, but we need the x-intercepts, and the x-intercepts come from factored form. We need to factor the polynomial, and I'll talk about that also. And you find the x-intercepts by letting y equal 0. Now the second thing we need is a y-intercept, and we find the y-intercept by letting x equal 0. And then we need to determine the correct end behavior, because that'll give us the basic shape of the function's graph. So we need the x-intercepts or zeros. Those come from the factors. We need the y-intercept, and we need the end behavior. So before doing all of that, I want to have a quick conversation about zeros of polynomials. This is an incredibly important topic in Chapter 3. Matter of fact, zeros of polynomials is going to be our topic in section 3.4 and 3.5, 3.4 and 3.5. So this is a very important topic in algebra, finding zeros of polynomials. So zeros of polynomials come from factors. So if x minus c is a factor of a polynomial, then that value c is what's known as a zero of the polynomial, which also means that it is an x-intercept. So 0, x-intercept, same thing, and they come from the factors of the polynomial. So to illustrate that, I've got a polynomial here, and the general form of this polynomial would have been x squared plus 2x minus 3. That's the general form. And we know it's a degree 2 from looking at that. So this is a degree 2 polynomial, but I've chosen to write it in factored form rather than the general form, because factored form is what's going to give us our zeros. The factors produce the zeros, and the zeros are the x-intercepts. So you can see here x minus 1 is a factor. So that means x equals 1 is one of my zeros or x-intercepts. X plus 3 is another factor, so x equals negative 3 over here is another x-intercept. So the zeros come from the factors. Okay, now over here I've got another polynomial. It's in factored form, but the general form of this would have been x squared minus 2x plus 1. So another second degree polynomial. You can see the highest exponent is 2. And we have two factors, but because they're identical factors, it produces the same zero of x equals 1. Now over here I've got a third degree polynomial, and incidentally the number of factors should be equal to the degree. So if a degree 2 polynomial has 2 factors, this one has 3 factors, so I know it's a degree 3 polynomial. And I've got 3 factors. One of them, x plus 3, is going to produce a 0 of x equals negative 3. These other 2 factors are identical factors, x minus 1, so it's going to produce the same 0 of x equals 1. What I'm trying to illustrate here is a very important distinction between zeros, x-intercepts, and what kind of x-intercepts we have. You can see here in these illustrations that x-intercepts are where the graph either crosses through the x-axis, like this x-intercept, the graph is crossing through the x-axis, or with this x-intercept, the graph simply touches the x-axis and bounces off of it. You can see on this picture here, we have both kinds of x-intercepts. We have an x-intercept where the graph crosses through the x-axis, and we have an x-intercept where the graph touches the x-axis and bounces off. The way that you determine what kind of x-intercept is what's called multiplicity of the zero. Multiplicity of the zero determines whether the graph is going to cross through the x-axis or whether it's going to bounce off the x-axis. If the zero has a multiplicity that's even, and the multiplicity is determined by how many factors there are that produced that zero. What I mean by that is, for example, this right here. There are two factors that produced the same zero of x equals 1. And so what you would actually write is this 0 is x equals 1 with multiplicity of 2. And same thing over here. Since this 0 came from two identical factors, we would say that the 0 is x equals 1 with multiplicity of 2. Now, if a 0 rather comes from a single factor that's not repeated, it has no multiplicity. So you don't need to state that. It's only if a 0 comes from repeated factors that you would state the multiplicity. And here's the thing to remember and to write down about multiplicity. If the multiplicity is even, then the 0 bounces. If the multiplicity is even, then the 0 bounces. If it has no multiplicity, meaning if it comes from a single factor, or if the multiplicity is odd, if the multiplicity is a multiplicity 3 or a multiplicity of 5, if it's an odd multiplicity, then the x-intercept crosses through the x-axis at that point. So again, there's two different kinds of x-intercepts. The x-intercept can bounce off the x-axis if it has an even multiplicity, like this one has even multiplicity because it comes from two identical factors, or the x-intercept can cross through the x-axis. That's if it comes from a single factor or if the multiplicity of the 0 is odd. Okay, so let's get then to actually graphing the polynomial using those three steps. First, we need to find the zeros or the x-intercepts, and then we need to find the y-intercept, and then we need to determine the degree of the polynomial so we can have the end behavior. So for part A here, I recognize, or we can recognize, that there are three factors. So each of those factors is going to produce a 0. So the zeros are x equals -1, x equals +1, and x equals +3. Each of those just come from the factors. Now, because none of these factors are duplicated or repeated, none of these zeros have multiplicity. And so each of these x-intercepts are going to cross through the x-axis. None of them are going to bounce off. Each of these are going to cross through the x-axis. So if we start to produce our graph, I have an x-intercept at -1, an x-intercept at +1, and an x-intercept at +3. Now the y-intercept, is found by letting x equal 0. In this case, all of the x's equal 0. So if I put a 0 in for this x right here, I would have 0 plus 1, which is 1. If I put in a 0 here for this x, I'd have 0 minus 1, which is -1. And then if I put in a 0 right here, for this x, then I'd have 0 minus 3, which is negative 3. So 1 times negative 1 times negative 3 is 3. So the y-intercept is the point 0, comma 3. Now, the end behavior of this function is what is the degree. Really, that's the same question, end behavior, degree. Since there are 3 factors, this is a degree 3. What I like to do is jot a quick sketch of just the end behavior. A degree 3 that has a positive leading coefficient, and I say it's a positive leading coefficient because there's no term here that's negative. So there is a positive leading coefficient, which means that the end behavior is right side is going up, left side is going down to negative infinity. So I know that on the right side of this graph, it's going up to positive infinity, and the left side of this graph is going down to negative infinity. So what we need to do now then is connect these two pieces of the graph, because remember the graphs are continuous and smooth, so there are no breaks or gaps. So if I'm traveling here on the left side of this function and trying to complete this function, I know that I'm going to pass through this x-intercept up to this y-intercept. Then I come down here and I pass through that x-intercept. I don't bounce at any of these because none of them have even multiplicity. And then I know eventually I'm going to have to turn back up and pass through that x-intercept. But the question is where exactly, how far down does it go before it passes back up? So the book does recommend, and I make the same recommendation, if you have a gap between zeros to where you have whole numbers you can plug in, like in this case x equals 2, if you have gaps between your zeros that are whole numbers, try to find out where the function is at those and plot some points. So if I plug in a 2 for x, 2 plus 1 is 3, 2 minus 1 is 1, and then 2 minus 3 is negative 1. So when x equals 2, I'm all the way down to negative 3. So I know I'm going to come down to negative 3, and then I can turn back up across the x-axis there and connect up with that side of the graph to produce the full graph. And that's really how it's done. You find the zeros with their multiplicity to determine if the x-intercept crosses or bounces. You find the y-intercept, then you determine the degree, and then figure out how those two ends line up or meet up. Okay. Part B. We need to find the zeros. And it can be, at least at first, a little deceiving. The question is, how many factors are there? And at first glance, you may say, well, there's 1, 2, 3. There are only 3 factors, but in actuality, there's a lot more. X plus 2 squared means that there's really 2 factors of x plus 2. And then x minus 1 cubed mean that there's really 3 factors of x minus 1 times x minus 1 times x minus 1. And then there's this factor of x. So there are 1, 2, 3, 4, 5, 6. There are 6 factors of this polynomial, which ultimately is going to mean it's a 6-degree polynomial. Now, these factors are going to produce the zeros. So the zeros come from the factors. This first factor here of x is going to produce a 0 of x equals 0. So that produces a 0 of x equals 0. This next group of factors here, x plus 2, is going to produce a 0 of x equals negative 2. And I'm going to say with multiplicity 2 because it repeats twice. This next group of factors, x minus 1 cubed, is going to produce a 0 of x equals 1, but it also has multiplicity of 3 because it repeats itself 3 different times, x minus 1 times x minus 1 times x minus 1. Now the significance of the multiplicity, remember, is it determines whether or not the graph is going to cross through the x-axis or bounce off the x-axis at those points. So sometimes, just to help students remember, I suggest that you actually write it out here with the 0. If it has an even multiplicity, it bounces. If it has an odd multiplicity, it crosses through, or if it just is a single 0 with no multiplicity at all, it also crosses. So it's not a bad idea to write it out just so you can remember. Now the y-intercept you find by letting all the x's equal 0. So I've put a 0 in for this x, and a 0 in for that x, and a 0 in for that x. I'm going to have 0 multiplied by 4 multiplied by -1, which is 0. So the y-intercept is the point 0, 0. And then the degree we discussed earlier, since this has 6 factors, it's a degree 6. And it's an even degree, which means the end behaviors are going in the same direction. Either they're both going up or they're both going down, and that's determined by the leading coefficient. The leading coefficient here is 1, positive 1. And since it's positive, the graph is facing up, so we know that the right side is going up and the left side is going up. So putting this all together, we have an x-intercept of 0, of -2, and positive 1. And then the y-intercept is also there at the same place as the x-intercept. The right side of the graph is going up to positive infinity. The left side of the graph is going up to positive infinity. So we need to determine how to connect these two sides. So I know that here at -2, we make the determination, all right, does it cross through or does it bounce there? And at -2, remember, it bounces. So when I get to -2, I'm going to bounce off the x-axis and come up. Now I know at some point I'm going to have to turn back down because I have to come to that point. The question is where, how high up does it go? And because we have this gap here between zeros, and the gap is large enough that I have a whole number there, -1, we do need to figure out where the graph is at -1. So if I plug in a -1 for all the x's, -1 plus 2 is 1, 1 squared is 1, and then -1 minus 1 is -2, and -2 cubed is -8. So it looks like it goes all the way up to 8 when x is -1. So it goes up to positive 8 rather, then comes back down. Now we're to the 0 of x equals 0, and it crosses there, so I know it crosses through. And it's eventually going to have to turn back up and come up to that 0. Now the question of how far down does it go, between 0 and 1 there are no whole values to plug in, there's no whole numbers, so you're not expected to plug in fractions or decimals. So just make a determination and say, all right, it's going to go down a certain amount and then come back up. You don't have to plug in any decimal values or fraction values there. Now we're to that 0 of x equals 1, and that one is going to cross through because it has an odd multiplicity. So it meets up with that portion of the graph, and there's the graph. Okay, we're to the last learning target here. Sometimes the polynomial, and actually, to be honest with you, most of the time the polynomial is given to you in general form like this. And so first, you need to factor the polynomial to find the zeros, and then you just do proceed as we've done with these last two examples. So with this one, I would factor out an x first. And then continue to factor that quadratic expression. To write the polynomial in factored form. So now that it's in factored form, we do exactly what we just did in the last two examples. We state the zeros. If they have multiplicity, we find the y-intercept and determine the degree. So the zeros are x equals 0 from that factor, x equals -2 from that factor, and x equals 1 from that factor. Now the y-intercept, if you would plug in a 0 for all of these x's, or if you plug in a 0 for all of those x's, it doesn't matter what form you use. You can use the general form or the factored form. You're going to get, if you plug in x equals 0, you're going to get y equals 0. So the y-intercept is the point 0, 0. Now the degree here, it's degree 3 because that was the highest exponent right there. So I know it's a degree 3 and it has a positive leading coefficient of 1. Positive leading coefficient means that an odd degree polynomial, the right side is going up to positive infinity and the left side is going down to negative infinity. So putting this all together on a graph, our x-intercepts of 0, -2, and 1, we have our y-intercept there already. Right side end behavior is going up to positive infinity, left side end behavior is going down to negative infinity. None of the zeros have multiplicity, so they're all going to cross. They're all going to cross through the x-axis. None of them are going to bounce. So connecting the left side to the right side, I know I'm going to cross through. And then because there's a gap between the zeros, I need to plug in that whole number. You only have to plug in if it's a whole number. So if you plug in a -1, you're going to get -1 times, and then -1 plus 2 is 1, and then -1 minus 1 is -2. So -1 times 1 times -2 is +2. So I go all the way up to +2 when x equals -1. Crosses through there at x equals 0, and because there's no whole number between 0 and 1, you don't need to plug in anything into the function. You just need to make a determination. All right, it's going to go down about maybe that far and come back up there to finish off your graph. And that should do it there for graphing polynomial functions. And really the culmination of this whole lesson would be perhaps an example like this where you have to factor, then find the zeros, find the y-intercept, determine end behavior. So some of the key things here to remember is the degree of the polynomial determines end behavior. If the degree is even, then the end behaviors are going in the same direction. If the degree is odd, then the end behaviors are going in opposite directions. Another thing to keep in mind is zeros are the same thing as x-intercepts, and the zeros come from the factors. If the factors are repeated, then the zeros have multiplicity. If the multiplicity is even, it means that the x-intercept bounces. The graph bounces off the x-axis at that point. If the multiplicity is odd, or if it has no multiplicity, then the graph crosses through the x-axis at that point. So those are some of the key things here to keep in mind when graphing polynomials.